Good morning. So this morning we will start with Dr. Abigail Fraeman. She is a research scientist at NASA's JPL. Her BS is in geology and physics is from Yale. PhD in Earth and Planetary Sciences from WashU in St. Louis. Her research focuses on using techniques of remote sensing to study geology, origin, and evolution of terrestrial planetary bodies in our solar system. Dr. Fraeman participates in several robotic Mars exploration missions, and her roles include Deputy Project Scientist for the MER Opportunity. And she also is working on the Compact Reconnaissance Imaging Spectrometer for Mars instrument and participating scientist on the Curiosity MSL. So welcome, Dr. Fraeman.
Wonderful. Thank you so much for having me, and thank you all for coming in at 9 o'clock on a Saturday morning. I'm so excited to have the opportunity to talk to you all today. And the original talk title I had was Mars Rovers Past, Present, and Future. I realized half an hour is barely enough time to do present, so I cut out past. I'm going to try and squeeze in future a little bit, but basically I just want to give you an update on some of the science that we've been doing with Opportunity and with Curiosity, and then also give a little bit of a look ahead to the Mars 2020 rover. So I'll start the talk by showing a slide that I'm sure many of you have seen before, and this is just a schematic of the robotic exploration plans that a lot of the government agencies, I don't think SpaceX is on here, but a lot of the government agencies have for future exploration of Mars. And as many of you are probably aware, we have a fleet of orbiters and rovers currently on the surface. So I'll be talking to you today about Opportunity, which is the rover that landed back in 2004 in Meridiani Planum, and then also Curiosity, which has been roving around since 2012, and then finish telling you a little bit about plans for sample return from the Mars 2020 rover. Excuse me. All right, so let's start off with Opportunity. Here is a picture of Opportunity, again landed back in 2004, and I like to think of Opportunity as a real good field geologist on Mars. The instrument suite on this rover were designed to perform science investigations that were primarily looking to answer the question of whether we could find any evidence that there was once water on the surface of Mars. Recall, this rover landed back in 2004. At this time, we didn't have any direct in situ evidence that there was ever once interaction of liquid water on the surface of Mars. So the tools on this rover are designed to investigate those questions. It has camera imagers, it has a rock abrasion tool, the RAT, that's kind of like a rock hammer. It has a microscopic imager that's designed to look at close-up textures, and it has some instruments to also look at the chemistry and the mineralogy. So really just a great robotic field geologist. Opportunity landed in this area, Meridiani Planum. It was an interesting area, primarily because from orbit we saw a spectral signature of a mineral called hematite, which is an iron oxide and can form in a variety of processes, but one of the ways that it forms is in the presence of water. We landed, found the hematite almost right away, looked at its geologic setting, realized it was deposited in water, and kind of realized that these plains that we'd landed on are representative of this playa environment. There were sediments that were kind of laid down through these sand sheets that had been moving through the area, and there was probably some intermittent wetting through groundwater upwelling, and that's what created the mineral signature that we saw from orbit. About 6 years into the mission or so, the rover ended up reaching this feature called, is there a pointer, by the way? Okay, I'll use the arrow if you guys can see this on the screen. This feature called Endeavour Crater, which is about a 22-kilometer diameter impact crater. And what is so remarkable about this crater is that through geologic mapping with the orbital data, we realized that the rocks in the rim of the crater were probably a lot older than the rocks in the plains. So by investigating the rocks in the rim of this crater, we were able to look at rocks that were placed in a much different time, in a different geologic setting, and there were rocks that might tell us something fundamentally different about the earliest climate of Mars's history. We spent a lot of time up here at this area called Cape York, looking where we saw spectral signatures of clays. We learned a lot about alteration and how these clays formed, kind of in these wet environments where water and rock kind of just sat around cooking in their own juices. We've learned a lot about impact processes. This is the first time we've really explored the rim of a large impact crater in another planetary body, so it has important implications for what we're learning about how these structures form. And then most recently, what I'm going to talk most about is our exploration of this feature on the side of the crater. We're kind of driving down the rim of the crater into the interior of the crater. Feature here called Perseverance Valley. And you might notice immediately, and this is what caught our eye, is it's a very distinct feature. It seems to kind of have these anastomosing or bifurcating channels. And we started to wonder what was the geological forces that shaped this feature. For reference, it's about 100 meters long. So here's a football field. Yeah, I know it's in yards, but it's close enough. Opportunity is currently about halfway down Perseverance Valley. And what we're doing is we're taking detailed morphologic images to try and look for evidence that might tell us how this feature formed. Before we got there, we kind of formulated 3 different hypotheses. First, it could be a dry avalanche, and this is basically just a rock fall. A bunch of rocks that fell down the mountain. There was no water involved. It carved out this channel. Generally, these occur on slopes that are greater than 30 degrees, and the slope of this feature is about 20 degrees, 15 to 20 degrees. So we thought this was pretty unlikely just because the slope's not steep enough to actually initiate this dry avalanche. The other 2 hypotheses that we really favored and that we're looking for morphologic evidence for are either a debris flow, which is a flow where you have solids and waters mixed. It's more solids than water, at least about 50-50. And there's certain morphologic indicators that we might be able to expect to find if it is a debris flow, these levees, maybe some snout formations, et cetera. And these can happen on much shallower surfaces. A third hypothesis that we considered was the idea about river transport. Is this actually a gully that was carved by some kind of stream where you have mostly water and just a little bit of rock? So we dove down in this crater. We're kind of tobogganing down the side of the rim of Endeavour crater. It's a one-way trip down this valley, looking for evidence of one of these 3 processes. When we got down into Perseverance Valley, what we found was that the morphology was very subtle. This is what it looks like kind of right in the middle of it. And you can see it's not this big, obvious dry stream bed. This is a very, very old feature. It's a very, very eroded feature. The things that we're looking at are subtle. One of the immediate things that we realized looking at the textures of the rocks at our feet was that they were very interesting. They appeared to be scoured. Here's a pan cam image that we took looking down, and you can see there's these interesting lineations, and we kind of scratched our head and wondered, what could this be? So we decided to do some closer investigation with the arm. So here's an example of the Rover pose trying to do this investigation, and you'll note not all of the wheels are on the ground, and this is just emphasizing that driving up and down this steep slope is a bit of a challenge. The actuators in the wheels right now, all of them, the drive actuators all work, but we have the right front steering actuator is towed in at about 8 degrees. That's been for several years now. But what happened right before we got into Perseverance Valley was the left front steering actuator also failed. It failed actually towed outward at 30 degrees, and that was really concerning to us that we couldn't straighten it because driving a Rover with 2 wheels kind of stuck like this is really hard. We sent a bunch of commands to straighten it. Nothing helped. We had a whole bunch of meetings wondering, okay, is there anything we can do that can make this work worse? We decided not. So we sent a bunch more commands to straighten it again, and then the last of those series of commands, it straightened. So it did work. We were able to straighten it, but we're now very cautious, and we don't ever want to steer it again because we don't want it to accidentally get stuck outward again. So we're now only steering with the back wheels. We use that to drive. You can imagine driving with back wheel steering when your arm is in front is a little bit difficult to try and position the arm exactly how you want it, but it's working well. But the terrain is challenging. We've popped a few wheelies, but the engineers who drive this are amazing, and they did manage to get us into position, and we got these awesome microscopic images right up close looking at these rocks and really looking in. What this seems to show is the evidence for wind fluting, and so there's these relatively erosant resistant little cobbles sticking out. This is probably a breccia, an impact breccia, and what you can see are these kind of streams around it. And what was the force that caused this? And if you map actually the direction of this, it's pointed uphill, and water does not flow uphill. So what this is telling us is these rocks were carved by wind, and what this is really telling us is it's emphasizing the important role of wind as a dominant force for shaping this feature. Something else that we saw when we drove down into the valley was evidence for faulting. We can see in orbital data kind of radial faults around the side of the crater rim, but remember I told you we're learning about impact processes, and we're learning kind of how these faults are found and distributed, and here's real clear evidence for a fault kind of driving into the valley and then looking back up towards the crest of the crater rim, and you can see that there's rocks of 2 different types on either side. So this is a fault. So we found evidence for radial faults. We found evidence for wind carving. So what is this telling us now about our formation hypotheses? Well, as I mentioned earlier, it's probably not a dry avalanche. It's too shallow. Could be a debris flow. We haven't found any obvious evidence that it is one, but we haven't found anything to exclude that. Could be river transport. The question mark there is a little bit smaller, simply because we have a really hard time explaining where the catchment area might be. We spent a lot of time investigating kind of the outside of the valley, looking for any evidence for a lake or anything like that. Saw nothing. So, could be probably less likely, but I think there's now a new hypothesis that we need to consider, that this may have been caused by wind erosion of a pre-existing fault. So we're still scratching our head, hoping to finish our way climbing down the valley and see, are there any sedimentary deposits that we find at the base? That might be where you expect kind of the most convincing evidence to be, so stay tuned. I will say one of the really cool things that we found in this area are these rocks that are unlike anything we've seen in Perseverance Valley. It's these weird kind of, we were calling them vesicular rocks, although they're probably not necessarily kind of vesicular in terms of a volcanic rock, but we're trying to understand what makes rocks that have these textures. They have an interesting chemistry. We're talking about whether or not they could be impact melt, although it's hard to kind of get the chemistry they have by melting the rocks that we see in the area. They could be some sort of interesting weathering feature. We get textures like this actually in rocks that you find in the McMurdo dry valleys in Antarctica and very cold, dry places like that. So, it's kind of this erosion that's exposing these new rocks that's totally unexpected and something we'd never seen before that we're puzzling. Recently, on February 15th, we celebrated a really important milestone, Sol 5000. It's just a number, but this mission recall was designed for 90 sols. So that's 3 months. I was in high school when it landed, and now I'm the deputy project scientist, so that can tell you how long it's been running. But we were really excited about this, and we actually took out our arm and, copying Curiosity's really successful selfies, used the microscopic imager, which does not have an infinite focus like Curiosity's does, to try and take a selfie, and it actually turned out pretty good. So this was the first time we'd seen an image of the vehicle since it was packed up and sent to the Cape for launch. So a really exciting milestone. Recently, as I'm sure you are all aware, we've had some issues with the dust storm on Mars. So this is a plot showing seasonality in the x-axis, and then a measurement called tau, which is basically its optical depth. It's a measure of how dark the atmosphere is, how much sunlight can transmit through the atmosphere. And what happened was this dust storm kicked up right around June, and we thought it might be a little regional dust storm. This is kind of the season where regional dust storms start. But the skies got really dark really quickly. This shows measures of tau value throughout the course of the mission. We have different years sitting on top of each other. This red area here, this was this big global dust storm we had back on Mars year 28 that caused a lot of issues for the vehicle. But what happened this year was it got dusty and it just shot up. And we have a tau value that we measured above 10, which is the highest tau value that any landed asset has ever seen on the surface of Mars. So I think this plot is really interesting because it just shows how fast it got dusty and how much dustier it was. This is a logarithmic scale, by the way. So it's way dustier than it was during the last dust storm. Here's an image of simulated what the sun would look like at the different tau levels. So tau 1 is about what we expect between this time of year, tau 1 to 1.5. The last dust storm we got up to around tau 5, between 5 and 7. And so back in June we were up around between 9 and 10. So the skies were basically black. Probably the only light getting to the rover was the diffuse light scattered from the atmosphere. When you have a solar paneled vehicle, not having the sun to charge the battery causes problems, and it caused problems to us. So on Sol 5111, Opportunity slipped into a low power fault, and in doing so, it kind of shut everything down, and is using its fault protection software to preserve just the most essential systems. We haven't heard from the vehicle since. We do see evidence from the orbital data and also from Curiosity on the other side of the planet that the skies are clearing. Tau value, we think, is now back down below 2, is the most recent measurement. And so the engineers have been working real hard to develop a strategy to listen. We think when we do hear from the vehicle, it'll be in a variety of different spacecraft faults, including possibly a mission clock fault, which is scary because the vehicle doesn't know what time it is. So it's programmed to wake up 2 hours after it gets enough power on its solar panels. We don't know how much dust is on the panels, so we don't exactly know when that'll be, but we have some good guesses. So kind of doing the best we can to try and recover the vehicle, and we'll see what happens. But it's, far surpassed its mission exploration lifetime. So we're real thrilled with the science it's done so far. This is just a beautiful artist concept of opportunity kind of on the rim of Endeavour Crater, kind of exploring Perseverance Valley. It's this tiny little blob here, and this is an image that was taken when we were further back, but it gives a nice sense of scale. All right, let's hop to the other side of the planet and Gale Crater and talk a little bit about Curiosity. Now, recall, if Opportunity is our robotic geologist on the surface of Mars, Curiosity is our chemist. Curiosity is a lot bigger than Opportunity. The science questions it was designed to address kind of go beyond, was there water on the surface of Mars, but now trying to understand, were these environments habitable? So understanding more about the chemistry of the water that was present, and also understanding what sort of materials does it have in the water, and does it have the building blocks that could have supported life? So there's two particular instruments inside the body of Curiosity, which are part of the reason it's so big. ChemIn, the XRD instrument, and then the SAM instrument, which is a gas chromatograph mass spectrometer, which can measure things like organics. Curiosity landed in Gale Crater, which is a 150-kilometer diameter crater near the dichotomy boundary. And the key feature of Gale Crater is this mound in the middle, which we've named Mount Sharp informally. The formal name is Aeolus Mons. And from orbit, we can see that this mound is layered. So the goal of the rover exploration is basically land at the bottom of this layered mound and then drive up the layers and go through time, go forward in time as we drive up this mountain and see what environments are recorded in these layers. This is Curiosity's traverse to date. Landed back down in Bradbury Landing. We worked our way across the plains, and then at about 2014, we got our first taste of Mount Sharp at Pahrump Hills, and ever since then, we've been driving up the mountain. Up is in this direction, and we're now currently exploring Vera Rubin Ridge. One of the key things that we've seen in all of the rocks, essentially in the Murray Formation, are these very fine planar laminated rocks. So here's an example looking kind of at the base of Vera Rubin Ridge at some of these rocks. You can see predominantly that there's these kind of planar, very fine scale laminations. There is a lot of stuff going on here, and actually there's a lot of fractures and secondary fluids cross-cutting all of this. So that's kind of these messy fractures that you see. But when we got up close and we looked at the rocks, you can see these are just beautiful examples of really fine-grained planar laminated rocks. So this is a target looking with the ChemCam remote imager and the MOLLE microscopic imager. Here's another rock again showing the planar laminations, and we've shot it with our ChemCam, our laser tool. This is one of my favorite rocks. It just looks really cool, the layering and then the dust that settles on the layers. Here's a zoom in of what that looked like. So what we've concluded, kind of based on the preponderance of evidence that we saw on the ground and also sort of the whole geological setting, that we can see that there are rivers kind of flowing into this crater. So we know there was water that was being transported into this crater. And then when you have these very fine-grained planar laminated rocks, you know whatever emplaced them had to be emplaced in a very low energy setting. So the best explanation we have, and what we think is consistent with all of the data we've seen to date through hundreds of meters of section, is the idea that these rocks were deposited in a lake. What's been really surprising is the fact that even though we've gone hundreds of meters up Mount Sharp, we're still seeing these very finely layered rocks. So what this is telling us is that, the lake probably existed for a very long time. If we make some rule of thumb estimations, kind of looking at typical sedimentation rates on Earth, to build a stack of rocks that high in that sort of depositional setting, you would probably need something on the order of 1 million years. So this lake was very long-lived, and this tells us something really important, that the climate of Mars had to be warm enough to sustain a lake for at least 1 million years, or on that time scale. So when you talk about kind of episodic bursts of warming in Mars's past, this is a really good kind of linchpin with observational evidence that those bursts had to have lasted quite a long period of time in order to permit this to happen. You probably have heard recently a press release of some of our very exciting results that just came out. These are based on drills that we did back in 2015, but the data are complicated, so it's taken that long to sort of go through and tease apart. But what Curiosity has discovered are evidence for organic molecules in these lake sediments. When I say organic molecules, I specifically mean carbon-bearing compounds. We don't know where these carbon-bearing compounds came from. They could be from, fossils of past life, but they they could also be meteoritic input. We see carbon-bearing compounds like this in asteroids and in meteorite samples we have from across the solar system. They could actually be from igneous processes too, from the deep interior of Mars. We don't have enough evidence or information to help us distinguish between these three different hypotheses. But what was really significant about these particular compounds was that they were sulfur-bearing. And what's special about having sulfur-bearing carbon compounds is that the sulfur acts as a really kind of strong bond with the carbon, and it makes these really tough. And so what's really cool is that these have survived for probably 3.5 billion years in this very intense radiation environment of Mars. And then the fact that they survived so well and we could find them today gives us hope for future missions to Mars, that there is evidence and there's a hope that we might be able to find more of these, that they may have survived in these environments in which this is something we were very unsure about. Another key result we found was finally starting to get a handle on this methane question. Over the last decade or so, there have been a lot of reports of detection of methane in the Mars's atmosphere. This is exciting because, again, methane could be created by biogenic processes deep in the subsurface, although it also can be created by a lot of abiotic geologic processes as well. When you have certain water-rock interactions, you can create methane. And the measurements were odd. We didn't really have an understanding how to explain them. They could have been also, again, delivered from impacts as well. But by doing very careful experiments with the tunable laser spectrometer on the rover, and in particular developing this method to enrich our measurements for atmospheric observations, to really nail down the uncertainties on these measurements and really get high precision, they were able to carefully look at the background measurements of methane that we see. We see these random periodic spikes, but we also see a seasonality in the background measurements. And the fact that we see this seasonality in just the general background methane of Mars tells us something important about the process. And kind of working through all the models, the most likely explanation from these models is the idea that this methane is being released from the deep subsurface, possibly percolating through fractures. You're getting a little bit more release in the summertime. And then you do have these periodic whiffs that might represent kind of the wind blowing through and concentrating it, still kind of thinking those things through. But this is really kind of the first evidence to help us distinguish between these mechanisms for what is making methane in Mars's atmosphere. And it's really telling us it's probably coming from Mars itself, which is pretty cool. Just to talk a little bit about what Curiosity is doing today, as I mentioned, we're exploring this feature on Mount Sharp. It's a very distinct layer in the orbital images, and this feature is named Vera Rubin Ridge, after Vera Rubin, the famous astronomer. And the key feature about this ridge is from orbit, we've mapped the presence of hematite, that favorite mineral that I mentioned in Meridiani again. And again, it's this idea that it may have formed in a water environment, and it also has potentially interesting implications about electron transfer and iron oxidation in these lake waters or secondary fluids that are moving through the mound. We're looking at this discovery. Our drill is online, and so we drove kind of to this area where we see the strongest hematite spectral signature, which is right around here, and we drilled, and we wanted to take a look at the mineralogy, both to confirm that our orbital predictions were correct and also to understand what were the other compounds that were there that would tell us something about how this hematite formed. I'll give a personal note. I actually mapped the distribution of hematite, the first detection, and talked about the implications of it as part of my thesis. So to be able to get there and drill it, this is a little bit nervous for me because we're actually proving whether or not I was right or wrong. And it's one of the few planetary science papers that we're going to be able to absolutely refute or not by going there and taking a sample. A little nervous, so we drove out there, we tried to drill where we saw the strongest hematite spectral signature. And what we found was this rock was insanely hard. We had the drill turned up to percussion level 5. It's a kind of a jackhammer drill, and we were kind of trying to get on the surface. You can watch the video of the drill, and there's stuff bouncing around, and we made it just a few millimeters into the rock before we decided our rate of progress is too slow, it's not worth trying to drill here. So this was really hard stuff, so can't test if I'm wrong or not, but then also, man, we can't see what else is here and really understand how this stuff formed, which I've been waiting to hear for 6 years or so. Perhaps that it's hard, it's not a surprise. This is a ridge, so here's another rendition by the same artist. Here's a view of Curiosity kind of sitting on top, and this is a ridge. It's sitting above the surrounding terrain. What a shock. It's harder than the surrounding rock. It's eroding slower. So we worked really hard to try and find a rock that might be a little bit softer, kind of looking at the erosional expressions of the rock and the large-scale morphology of the ridge. And on our third try, We got one, we drilled, we got the data down in the middle of this week, so we're kind of churning through that. Things are looking good for my predictions, so I'm very happy about that. And we're learning a lot of other new things, so stay tuned for the results. Woohoo! And in the last 2 minutes, I'm just going to talk a little bit about future rovers, and that's, of course, the Mars 2020 rover. This is launching in 2020. It will get a new name. But this rover is the collection rover. So the idea of this rover is that it's going to be the first step of Mars sample return. You know, this figure is a little bit unfair where I just kind of put a hobo stick on the arm, but it's actually quite this really complicated caching system where we're going to drill into the rocks, we're going to make a core, we're going to make these hermetically sealed tubes, and we're going to send these tubes back to Earth. Here's a zoom in of what the tubes look like, but this is all part of a notional sample return architecture where we're going to drill, we're going to send it to a MAV. This is going to be a subsequent mission with the MAV and the Fetch rover. It's going to launch. We're still deciding if that's going to be one mission where it launches and returned to Earth, or 2 missions where it launches and then we send something else to grab it. But really trying to get these samples back, and it'll be important because there'll be samples from Mars in a known geologic context. And in particular, we're looking at 3 possible geologic settings to collect these. The first is an ancient delta setting, Jezero crater, which is both composed of rocks from the ancient Martian crust and also might be a great place to trap and store organic molecules. So if you're looking for life, this could be a wonderful place to look. The other site is Northeast Syrtis, which is just kind of around the corner from Jezero, and this is this really ancient Martian crustal rock. It's from a period of time in Mars that we haven't yet visited with the rover, and these rocks would tell us something fundamental about how the atmosphere and the climate of Mars were that period of time. And then the third site are the Columbia Hills sites. This is the site where Spirit was exploring, and we found these really interesting silica digitate structures that look very similar to some structures we see at hot spring environments on Earth. And excitingly, those are caused by biotic processes. So, you know, if you're looking for a biosignature, the argument is we may have already found them, so this might be a great site to go and bring those back. So I will leave you with that. Stay tuned. You can check out more information about Mars 2020 at that website, and all the Mars missions that, robotic missions that are currently at Mars through NASA at mars.nasa.gov. So thank you very much.
I'll go.
Question about opportunity. Is the rover parked on a slope, such as you might do to prepare for winter? And if so, are we expecting that passing wind might help to move dust off the panels?
Yeah, great question. We parked on a slope. It's about 11-degree northerly tilt. So we're in just south of the equator, so it's favorable for our solar panels. And because we're on the rim of this crater, we've seen a lot of winds kind of blowing up and down and into the crater. And we're the time of year where we do see these these seasonal cleaning events. So we're crossing our fingers. We're in a good position for something like this to happen.
If there's funding for a successor to Mars 2020 and you could pick, what capabilities would you like to put on it, and where would you like it to go? What would you like it to do? What do you think is the next target you'd like us to focus on?
Excellent question. So first, I would actually like another orbiter. The orbiters we have are aging. The last one that NASA sent, at least, was the Mars Reconnaissance Orbiter in 2005. And then there's also the Maven rover orbiter, but it's orbited not quite right. So a new orbiter to serve as a telecom relay for assets on the surface, and then also some new instrumentation to sort of follow up on some of these orbital discoveries that we've made that we want more information about. In terms of where to send the next rover, Mars is a really interesting geologically diverse planet, and I think MER in particular has done an awesome job kind of doing a first cut at looking at the geology. So I would love to send a suite of dozens of kind of MER opportunity class rovers to dozens of sites. There's so many places to go, and you go to these landing site workshops where we're trying to pick where the next rover is going to land, and there's so many good ideas, and they're all good. So more rovers on Mars.
Hi, Abby.
Hi, Lou.
When is the what is the in situ measurements plan for the 2020 rover?
Yeah, so it has a suite of instruments that are designed to get into the really fine scale structures of the rock. So it's two kind of premier instruments on the arm are called Pixel and Sherlock. Pixel is going to look at the elemental chemistry of the rocks, its X-ray fluorescence, and it's going to do it at like the micron scale. So really go point to point and see how each grain varies in chemistry. Sherlock is a Raman spectrometer, and that's going to look at organics. It's in the deep UV, so it's going to be able to detect organics. So we're actually excited. We think the abundance of organics and the kind that Curiosity found would be able to be detected by the Sherlock instrument. There's also an instrument called SuperCam, which is a laser similar to what we have on Curiosity, but it's kind of souped up and has more technologies. And then Mastcam Z, of course, which is going to be the awesome camera, which will be like the cameras on Curiosity, but they'll have a zoom capability. The engineering cameras on 2020 are going to be in color, so no more black and white photos, which is going to be awesome. Color really helps when trying to figure out the geology. There's an instrument preparing for human exploration called MOXIE, which is going to ingest atmosphere and I think trying to process O2 from the atmosphere, so trying to think about can we actually do these things in the Martian atmosphere in the setting that we hypothesize could happen to prepare for human exploration. And then I think there's some weather instruments as well, the META instrumentation. And I hope I'm not forgetting anything. Oh, yes, and the Mars helicopter will be on 2020 as well, the recent announcement. I'm excited about the helicopter. It's going to be a tech demo, but basically engineers have figured out you can fly a helicopter in Mars even though it's a low atmosphere. If you make the blades big enough, it can work. They've done it in test chambers here on Earth under kind of reduced pressure, and so they're sending the helicopter with 2020. It's going to do a few test flights, and if successful, I think this will open a whole range for possible capabilities for future robotic exploration. We can help extend our drives by scoping out drive meshes. We can explore larger areas much faster, so I'm really looking forward to that. All right, thank you all so much.